Exercise 67 is an example of an exercise where we will have to find rates of changes. This is going to be among the most difficult concepts and problems in the entire year. Next section is also about that. So, 67, angular rate of change. An airplane flies at an altitude of 5 miles toward a point directly over an observer. Consider theta and x as shown in the figure. Write theta as a function of x, and then, knowing that the speed of the plane is 400 miles per hour, find d theta dt when x equals 10 miles and x equals 3 miles. We'll only do the x equal 10 miles because then 3 miles is just about the same, but in exchange we'll ask an additional question that's more about thinking. So here's the observing person, and the plane is coming straight towards that person. So first thing we need to understand and accept is that if the speed of the plane is 400 miles per hour, it means dx dt is negative 400. So as the plane moves forward, x is becoming smaller and smaller, so the rate of change of x, dx dt, is a negative number. Dx dt equals negative 400 miles per hour. Also, what's very important is to understand that when the plane approaches, the angle, imagine yourself looking at a plane in the sky and the plane is coming towards you. If you just stare at the plane, you're going to have to lift your neck more and more and bend your head backwards. So theta is increasing. When the plane is here, theta is bigger. So what that means, if theta is an increasing function, d theta dt is a positive number. And this is what we're supposed to find when x equals 10 miles. Alright, so let's see what we can do. Here's a sketch of the situation. We have x, we have theta, we have a height of 5. I didn't put any units for the moment. The speed is 400, so the velocity is negative 400. We write it dx dt equals negative 400. X equals 10. Okay, so we need to find an equation that ties all these variables together, and the clear one to choose is tan theta equals opposite over adjacent 5 over x. And since we're interested in knowing how quickly the angle theta is changing, what we're looking for is d theta dt. What is the rate of change of the angle? So quite clearly we want to take the derivative of that to make d theta dt appear in an equation. So the derivative of tangent theta is secant squared theta times d theta dt. Again, because I'm differentiating in terms of a variable t that is not theta, I need to multiply by d theta dt. On the other side of the equality, notice that 5 over x is actually 5x to the negative 1. So rather than using the quotient rule, u prime v minus uv prime over v squared, we can just take the derivative of that using the simple power rule for derivatives. So the derivative is negative 5 times x to the negative 2. But we're not done, because once again we're differentiating in terms of t, not x. And therefore it's times dx dt. So we have lots of letters in here, and we need to now check which ones we know and which one we don't know. This is the one we're looking for, and let's see what I can substitute. And maybe I'm lucky and I already have everything, maybe I'm not lucky and I need to work a little bit more. So d theta dt, negative 5, x is 10, so this is 10 to the power of negative 2, which is 1 over 100. dx dt is negative 400, and then the secant squared of theta. Do I have theta? No, I don't. Okay, that's too bad. I need to make a little extra effort to find theta. How am I going to find theta? I'm going to use the original equation. So that's quite fascinating. I'm using the same equation twice. Once to find the derivative and once to find the specific value of theta. Tangent theta equals 5 over x. At that very specific moment that I'm looking for, tangent theta is 5 over 10. And therefore, theta is arctan of 5 over 10. So, secant squared of arctan of 5 over 10. And now I have everything I need, so I can solve for d theta dt. It's equal to all of this divided by secant squared of arctan of 5 over 10. And what I get is 16 radians per hour. How do I find the units? You need to read what the variables are in the rate. Theta is in radians, t is a time in hours, so it's radians per hour. There's another way to solve this exercise, because in fact this section is all about inverse trig functions, and we barely used an inverse trig function. We used it here, but we didn't really do anything more than that. We didn't differentiate an inverse function. So what we could have done instead, starting over, x theta 5 dx dt equals negative 400, x equals 10. When we set up tan theta equals 5 over x, we could have solved theta equals arctan of 5 over x. And in fact, that's the intention they had. Question A is find theta in terms of x. So this is the real correct answer to question A. Theta equals that. And now, if I take the derivative, d theta dt is equal to the derivative of arctan is 1 over 1 plus 5 over x squared multiplied by the inside derivative. And remember, 5 over x is easier to differentiate if I write it as 5x to the negative 1, so it's times negative 5x to the negative 2. And then I need to multiply again. It's the inside derivative because we are differentiating in terms of t. So from here I can just plug in x equals 10 here and there. I can plug in dx dt equals negative 400, and of course I should find the same result. Now the question that I want to ask is, what if x was equal to 3? Would it be a larger number or would it be a smaller number than 16 radians per hour? Think about it for a second and then I'll give you the answer. The answer is that d theta dt should be a smaller number, a larger number, sorry, d theta dt would be larger than 16 at x equals 3. And the reason is we are now much closer to the person. Now there's only 3 miles horizontally between the person and the plane. So just think about it in real life. If you're staring at a plane in the sky, if the plane is far, far off at the horizon, you're not going to need to move your head very much. It's so far away that it doesn't feel like it's approaching very much. But if the airplane is almost above you, you can see it move much more, and the rate at which you will need to change the angle of your head is going to be much greater. So the second exercise I want to talk about is exercise 75. Determine whether the statement is true or false, and basically justify. The slope of the graph of the inverse tangent function is positive for all x. Okay. The slope of the inverse tangent function is positive for all x. Is that true or false? So we have y equals arctan of x, and the question is y prime greater or equal to 0 for all x? Yes or no? We can approach this in two ways. We can just think about it graphically. We know that the graph of tangent, well, it's not as, the slope is not as, it's not 0 here for tangent. It's more like this. The graph of tangent, roughly, y equals tan of x. So the graph of arctan x is like that, with horizontal asymptotes at negative pi over 2 and pi over 2. So visually, on the graph, we can see that yes, the slope is positive for all x. This graph is always going up. That's the first way to answer. The second way we can answer this question is to calculate the derivative y prime. Since we know that y equals arctan x, the derivative is 1 over 1 plus x squared. And if we think about any value of x, x squared is always going to be positive or 0. So 1 plus x squared is always going to be a positive number. So I have a positive number divided by a positive number. It's always going to be positive. So yes.